Hello students, today we're going to cover section 4.5, linear approximations and differentials. So the first thing that we want to do is imagine taking a curve that we're used to in some form, shape, or fashion, and we pick some random point on that curve. We can call that point P. If we draw the tangent line to the curve at that point and zoom in on it as many times as you want, what we're going to end up finding is that the more we zoom in on that point, the more and more the curve approximates a straight line. So let's take a look at what that looks like. So as we zoom in on this point, you can see that the tangent line at that point approximates the curve itself the closer we zoom in on that point. And you can see it doesn't really matter the point that we select. The more we zoom in on that point, the closer the curve approximates a straight line. Now on the other hand, if we consider a function that has a cusp at some point Q, it doesn't really matter how much we zoom in on the cusp, it's never going to approximate a line. Now this has to do with the basic fact of differentiability. The original curve that we looked at was differentiable at the points that we were discussing. Now comparing that to the second function that we looked at, we can see that since there's a cusp at this function at Q, the function's not differentiable at Q. And so realize that the descriptions that I'm about to go through with linear approximation require that the function be differentiable at the point in question. So the idea that we just covered suggests that if we zoom in on a graph of some smooth function at a point that is differentiable, then the curve and the tangent line really become so close to the same thing that there's not much difference. So if we assume that the function is differentiable on some interval containing a point A, the slope of the line tangent to the curve at the point A, and then using the value of the function at A as its y-coordinate, is the derivative of the function at the given point. So here we can see that the equation of the tangent line is y minus the value of the function at A equals the slope, or the derivative of the function at A, times x minus A. Or we can say that y equals the value of the function at the point plus the derivative of the function at the point times x minus A. And we're going to call this function L of x, or the linear approximation to f at A. So if the function and the derivative are easy to evaluate at the given point, then the value of f at points near that point is easily approximated using that function L of x. In other words, the function is about the same thing as L of x. And so the closer we are, the better our approximation is. So as we move x closer and closer, we can see that the value of the line and the value of the curve are really close to the same thing. In fact, the closer we get to that point, the better our value is. You can see if we change A here, the value of x as we go further from A, the approximation and the actual value are going to be pretty far apart. But if I take x close to A, then the value of the function and the value of the approximation are really close to the same thing. So this brings us to our first definition, the linear approximation to f at A. So if f is differentiable on an interval containing the point A, then the linear approximation to f at A is the linear function described earlier. So let's go ahead and take a look at our quick check. We want to sketch the graph of a function f that is concave up at a point a comma f of A, and then sketch the linear approximation to f at A. Is the graph of the linear approximation above or below the graph of f? Okay, so here I'm going to sketch the graph of a function that's concave up. So here's my concave up function, and I'm going to define point A on this function somewhere within the interval. The quick check then goes on to say to sketch the linear approximation to f at A. So we want the tangent line of this function at point A. So based on that, I'm going to look and say that that's going to be somewhere in that neighborhood. So here's my linear approximation, or this is L of x. So the question asks, is the graph of the linear approximation above or below the graph of f? So in this case, we can see that with a concave up function, the linear approximation, or the linear function that's tangent at that point, is going to be below the function. So then our first example talks about useful driving math. So if we suppose that we're driving along a highway at a fairly constant speed and record the number of seconds it takes to travel between two consecutive mile markers. If it takes 60 seconds to travel 1 mile, then your average speed is 1 mile every 60 seconds, or 60 miles per hour. Now if we suppose that we travel 1 mile in 60 plus x seconds, in other words it takes 62 seconds, then x is 2. And if it takes 57 seconds, then x is negative 3. So the speed function here is 3,600 divided by 60 plus x, or, for ease of things, 3,600 times 60 plus x to the negative 1 power. And this speed function will give our average speed in miles per hour if we travel 1 mile in x seconds more or less than 60 seconds. In other words, if we travel 1 mile in 62 seconds, then x is 2 and our average speed is s of 2, or about 58.06 miles per hour. If you travel 1 mile in 57 seconds, then x is negative 3, and your average speed is s of negative 3, or about 63.16 miles per hour. And the question says, since we don't really carry a calculator while driving, we need an approximation to this function, so we're going to use the linear approximation formula to derive a formula. And here you can see that the idea is to find the linear approximation to s at point 0, so we use the chain rule and find the derivative of the original speed function. We note that s of 0 is 60, and the derivative at 0 is negative 1. So using the linear approximation formula, we find that s of x is approximated by L of x, which is 60 minus x. So if we travel 1 mile in 62 seconds, then x is 2, and our average speed is about 58 miles per hour, which is really close to the exact value. If you travel 1 mile in 57 seconds, then x is negative 3, and your average speed is L of negative 3, or 63 miles per hour, which again is really close to the exact value. So let's take a look at our quick check. In example 1, suppose you travel 1 mile in 75 seconds. What is the average speed given by the linear approximation formula? What is the exact average speed? And explain the discrepancy between the two values. Quick check 2 asks, what's the average speed given by the linear approximation formula? So again, remember in this case we have L of x. Our linear approximation is going to be 60 minus x. So remember x here is the difference between 60 and the speed we're traveling. So in this case we have 60 minus the difference, which is 15. And so 60 minus 15 is 45, so our linear approximation says that we're going approximately 45 miles per hour. The second part asks us to find the exact speed, so we're looking for s of x. So S of x is 3,600 over 60 plus x. So in this case, we're looking for 3,600 over 60 plus x, where x is 15, so we're looking for 3,600 over 75. And 3,600 divided by 75 is 48 miles per hour. So in this case, we can see that the two formulas give a discrepancy of 3 miles per hour. And the reason for this 3 mile per hour difference is because we started at 60 and 75 is now far enough away from 60 that we're getting that discrepancy. Example 2 talks about linear approximations and errors. So we want to find a linear approximation to the square root of x at x is 1 and use it to approximate the square root of 1.1 and to estimate the value of the square root of 0.1. So first we're going to construct the linear approximation. So we find the value of the function at a. So f of a is going to be the square root of 1, which is 1. And we need to take the derivative. So we have 1 over 2 times the square root of x. And so the value of the derivative at 1 is 1/2. So here we have our linear approximation, 1/2 times x plus 1. So here we can see we have the tangent line to the function at a equals 1. And we're trying to use that to approximate the value when x is 1.1. So we can see that the two values are extremely close together. And by plugging 1.1 into this equation, we have 1.1 plus 1, so 2.1, and we want half of that, which will give 1.05. And if you plug 1.1 into the square root function, we can see that the value that the function actually gives at that point is 1.0488. So the linear approximation has an error of about 0.1%. Now going back, because our tangent line is above the function, we're always going to have an overestimate. So we know that we probably want to adjust our value down, which can be seen by actually plugging in the function. If we try to use that same linear approximation for the square root of 0.1, we end up with L of 0.1, or half of 1.1, which gives 0.55. But a calculator will tell us that that square root is actually 0.3162. So our approximation is off, and the reason that it's off is because if we try to approximate using this linear approximation that we created the first time, we're going to be off by quite a wide margin. So rather than using a tangent line at 1, we might want to use a tangent line at 0.09. Now you can see our tangent line, or the point in question, is far closer to what we're actually looking for, so our approximation will be much more accurate. So let's take a look at our third quick check. Suppose we want to use a linear approximation to estimate the square root of 0.18. What's a good choice for a? Quick check 3 asks us, suppose we want to use the linear approximation to estimate the square root of 0.18. It says, what's a good choice in this case for a? So we want something close to 0.18. So something close to 18 over 100. And since we're taking a square root, it'd be nice to have both the numerator and denominator be a perfect square. So if I had to say what I would choose probably 16 over 100. Because that's going to be 0.16, which is going to be very close to 0.18. And the square root of 16 over 100 is fairly easy to find. That's going to be 4 over 10. So we want those things to be kind of easy to work with. So I would choose 0.16 for my value of a. In example 3, linear approximation for the sine function. Find the linear approximation to the sine function at x equals 0 and use it to approximate sine of 2.5 degrees. First, we construct our linear approximation. So our linear approximation is going to be the value of the function at 0, which in this case is 0, and then the derivative of the function at 0. So we have cosine of 0, which in this case is 1. So here we get 0 plus 1 times x, which is just x. Now, quick note here, before we use the linear approximation function to approximate sine of 2.5, we have to convert it to radian measure, because the derivatives require trig functions to be in radians, not degrees. So 2.5 degrees is pi over 72. So we plug pi over 72 into our linear approximation and get 0.04363. And if you plug in a calculator sine of 2.5 degrees, you get 0.04362. So you can see that our linear approximation is extremely close. Quick check 4 asks us to explain why the linear approximation to f of x at cosine of x is 1. Remember, cosine is a trig function that is a periodic function, and it looks something like this. Well, taking a closer look at what's going on here, we can see that the tangent line at x equals 0 is going to be a horizontal line, so the linear approximation at that point is going to be 1. Now realize that this linear approximation isn't going to be good for a whole lot, because as the function gets away from those points, we can see that the value of the function is certainly not 1. But really close to that point, really close in there, we can see that the function is in fact going to be very close to 1. In fact, the value of the function at 0 is 1. And since in this case that's a local maximum, that's why the linear approximation is a horizontal line. So let's take a look at a variation on linear approximation. So we have said that linear approximation of the function can be described as the value of the function at a given point plus the derivative of the function at that point times x minus that point, where a is fixed and x is some nearby point. So by rewriting it so that we have the change in y, or f of x minus f of a, call that delta y, we're going to approximate the derivative of a and x minus a, so this is really just the change in x. What this allows us to do is show the relationship between the change in x and the change in y. We can see here as I drag the change in x closer and closer, the change in y becomes closer and closer as well. In other words, as our point in question becomes closer and closer to the point that we're trying to describe, the linear approximation gets better and better. The further away we go, the more error we're going to have. So supposing f is differentiable on some interval containing a, the change in the value of the function between 2 points a and some other point slightly bigger than a is going to approximately be the derivative of that function at a times the change in x, so long as a plus delta x is inside the interval. So if we want to approximate the change in the function x to the 9th minus 2x plus 1, when x changes from 1 to 1.05, we say that the change in y is delta y, which is approximately the derivative of a times delta x, where a is 1, the change in x is 0.05, and the derivative is 9x to the 8th minus 2. So we substitute these values in and find that delta y is about the derivative at 1 times 0.05, or 7 times 0.05, which is about 0.35. And we'll say that if x increases from 1.00 to 1.05, then y increases by approximately 0.35. And we can do the same thing geometrically. We can say the surface area of a sphere is 4 pi r squared. So the change in the surface area when the radius changes by delta r is the change in surface area is going to be about the derivative of s at a times delta r. So we substitute in. We plug in 4 to 3.9, so that's negative 0.1. So we get 32 pi times negative 0.1, and say that it's negative 10.05, or the surface area is approximately negative 10 square meters. And so since it's negative, that's reflecting a decrease. So to summarize, we approximate f near a by using f of x is about L of x, which we said was the value of the function at a, plus the derivative of the function at a times x minus a. And if we want to approximate the change in y in the dependent variable when x changes from a to a plus delta x, we say that delta y is going to be about the value of the derivative at a times delta x. So finally we have the ability to talk about differentials. So we've talked about delta x and delta y. The change in the linear approximation we call the differential, or dy. So if we consider a function which is differentiable on an interval containing some point a, if the x-coordinate changes from a to a plus delta x, the corresponding change in the function is exactly going to be f of that value, a plus delta x, minus f of a. But if we use the linear approximation, the change in L as x changes from a to a plus delta x is going to be delta L, which is going to be L, a plus delta x minus L of a. And so then here we've broken it down to L of a plus delta x and L of a. And so we have f prime of a times delta x. So now we've created a new problem. We need to be able to distinguish between delta y and delta L, because in this case we have two changes in y variables really. So we introduce new variables which we're going to call differentials. So the differential dx is really just the change in x, or delta x. And the differential dy is the change in the linear approximation now. So now this is really delta L. So now we can say that delta L equals f prime of a times delta x. But if we use the new notation, we have dy equals f prime of x delta x. So if f is differentiable on some interval containing x, then a small change in x is denoted by the differential d of x, and the corresponding change in the function is approximated by the differential dy, which is f prime of x dx. So this is Gottfried Leibniz's notation, one of the co-founders of calculus. So here, by changing dx, we can see what happens to delta x, dy, and delta y. So finally, example 5 asks us to use the notation of differentials to write the approximate change in 3 cosine squared x given a small change dx. So in this case, the derivative of 3 cosine squared x is going to be negative 6 cosine x sine x, or negative 3 sine 2x, using our trigonometric identities. So in this case, dy equals f prime of x dx, or dy equals negative 3 sine of 2x dx. So here we can see by increasing x from pi over 4 to pi over 4 plus 0.1, then dx is 0.1, and we can plug in 0.1 here, and show that dy is negative 0.3. So a change in x of 0.1 creates a decrease in y of approximately 0.3. And that concludes this lecture on section 4.5, linear approximation and differentials.